Now that we have discussed Lewis bonding theory and Vesper theory, we can start putting these to good use. And by good use, I mean predictive power. It's getting a picture of an atom in 3D allows us to understand how its electrons are actually distributed around the molecule, which will tell us how it'll interact with other substances like water or oil. It tells us about polarity. So like in a daily life sort of example here, the shape of your molecule and the distribution of electron density around it tells us if it will be a water soluble thing or a fat soluble thing. So when I think about my vitamins that I take, I'm like, oh, are they water soluble or fat soluble? That kind of like changes how my body interacts with it, right? So that's where this is going to give us power to predict that. So to do that, we have to talk about molecular polarity. So here's what it is. When two atoms form a covalent bond, like we discussed about electronegativity, one element may have a much higher electronegativity than the other, which means it has an ability to attract electrons to it better. I don't know why I'm so negative, but I've always kind of thought of this as being electron greedy. It's like and maybe this is because I have siblings. It's like the kid at Halloween that gets all the candy, or Easter egg hunt. They get all the Easters, or I'm sorry, I'm coming up with Christian Americanized holidays here for examples. It's just part of my background. But I think we all have some piece of some part of our life that could be like, oh, the example that I have of someone who's just trying to get all of the things. And so in this example, fluorine is trying to get all of the electrons. It is our most electronegative element. So it's just really good at attracting electrons. I guess the more positive spin is like fluorine's the popular kid amongst the electrons, and like the electrons just want to hang out with it. And so what happens in the molecule where we have a hydrogen and a fluorine bonded together is that the electrons are not evenly distributed at all. In fact, they are more attracted to that fluorine atom, and so they're around the fluorine more. They have a greater probability of being found closer to the fluorine nucleus. And so that creates an uneven distribution of electron density in the molecule. And the second the electrons tend to be on one side more than the other of the molecule, it creates a dipole moment. It creates a partial positive charge and negative charge across the molecule. And then remember, so much of chemistry is just founded on the attraction of opposite charges or the repulsion of like charges. Then it's going to change how it interacts with other molecules because it'll have this slightly positive and slightly negative end. So it can interact with ions, right? Or other partially charged molecules. So let's take a look at this step by step. So I've got hydrogen and fluorine, a super simple molecule. I look up my electronegativities from a table. Back in the day when we walked uphill to college in the snow, both ways, they didn't give us electronegativity values. They just gave us the general trend and you compared. So, enjoy your table. And so for hydrogen, we have 2.1, and for fluorine, we have 4.0. So this 4.0 is larger than the 2.0. So the fluorine is more electronegative. So the electrons will spend more time around fluorine. Another way of saying that is the electron density will be greater around the fluorine. So that's going to create a partial negative charge at the fluorine and a positive charge at the hydrogen. And the way we represent that is with a delta symbol to mean partial. So partial positive charge means delta plus, and partial negative charge means delta minus. And to represent a bond like this that's polar, we have to have both. You can't have one without the other. And so the hydrogen's the partial positive, and its counterpart is the fluorine that's partially negative. Another way to represent this is with a dipole arrow or a dipole moment arrow, and that's right here, this red arrow. And what you're doing here is showing the partially positive end has the plus part of the arrow, and it's pointing to the partially negative end. So it's pointing to the more electronegative element. Either of these work. I find that students that are first learning this with the delta positive and minus tend to put them across the molecule rather than on a bond. And so these need to be associated with two elements in an actual bond. And so every bond will have a delta plus and a delta minus. So if that sounds confusing, it might be easier to do the arrow, but whatever works. So now in this simple case where we just have these two elements that are bonded together, we can get a picture from this dipole arrow of what is happening in the overall molecule. And so what's happening is this right here, where this is our hydrogen and this is our fluorine bonded together. And this increase right here, this is showing more electron density. And so this is creating that partial negative, and that deficit over by the hydrogen is creating that partial positive charge. And this then becomes a polar molecule. And that's going to mean a lot later. It's going to mean when we talk about intermolecular forces, it's going to mean that it can dissolve in water, for one. Water is polar, like dissolves like. So our polar molecules will dissolve in water. And so when we are looking at more complicated molecules, what we're going to do is we're going to look at the combined effects of all of these polar bonds. So we're going to take all these dipole arrows and try to combine them and say, what is the average of everything that's happening in this molecule with these polar bonds, polar covalent bonds? And so the overall polarity of the molecule will be dictated by the vector sum of those dipole moments. And so we usually represent that with a dipole arrow that's like usually like, so for this, I would represent its dipole moment for the whole molecule like this. And it's such a simple molecule that it actually looks the same as the dipole moment across the bond. Let's look at some more complicated ones though. All right, so these are still simple molecules, but we'll take a look at these. They perfectly illustrate two examples here. So I'm actually going to start with the water because we were just talking about this combined effect and the vector sum. And both of these are going to show a vector sum and a different effect. So the water is going to have a net dipole moment. It's going to be a polar molecule. And this arrow that's dotted right here is showing the overall dipole moment of the molecule. So here in blue, I have the polar bonds. That hydrogen has an electronegativity of 2.1 and the oxygen has a 3.5. So I have a polar bond. Remember, if it's less than 0.5, it's nonpolar. If it's 0.5 to 1.9, it's polar. If it's greater than or equal to 2, it's ionic. So in this case, we're looking at this range right here for polar bonds. So I have these polar bonds on my hydrogens that are going like this, right? So some part of that is going to cancel out, but some of it will add up. So if I take the vector sum of those two right here, it would go kind of in between them. So here's kind of our vector sum. So for our oxygen and hydrogen, we have a dipole moment, two dipole moments going in this direction. I can break that down into the XY components of that vector. And I can see that these two cancel out because they're pointing in opposite directions, whereas these two add up because they're pointing in the same direction. And so that'll give me an overall dipole moment that's the sum of the two that are pointing in the same direction. Looking at carbon dioxide over here, it also has two polar bonds, but this one's going to be nonpolar. Sorry, switching pen colors. Because those two dipole arrows, they're pointed 180 degrees apart in totally opposite directions. And so they cancel each other out. The vector sum of these is 0. And so we have a nonpolar molecule that has two polar bonds within it. It means it has an even distribution of unevenly distributed electrons within two separate bonds, which is like, and so here is my grotesque analogy to help with this. Have you heard of being drawn and quartered? It's like an old way of executing people. What happens is you tie to a person's limbs, their hands and legs, horses. So I'd be tied to 4 horses, right? And what happens is the four horses run in opposite directions and the limbs get pulled from the body and the body falls flat. And to me, this is the perfect example of a nonpolar molecule that has polar bonds, right? So I'm actually going to stand up, hold on, to demonstrate this. Okay, so I've got, if I have my, you can't see my legs. That's okay. So if my arms are being pulled, if I have my hands are more electronegative elements, or they're tied to horses, and they're pulling away, that electron is getting pulled up and away, I would get pulled up to my ceiling, right? And I would have a polar moment. But let's say my feet and my arms, I'm standing in a tetrahedral arrangement right now, even though you can't see it. They're going to get pulled at the same time. My arms are going to get pulled up while my legs are getting pulled down. And the effect is I'm going to go nowhere. My limbs will be pulled from my body and I'll die, but I'll be a nonpolar molecule. Maybe that helps. Maybe it doesn't. So let's walk through the steps to predict polarity. So like everything, we're starting with the Lewis structure. I'm going to go back to that same example we've been working on, which is our ammonium. That has been our kind of introduction to all of our concepts here. So I draw my Lewis structure, and then I determine the molecular geometry, which is trigonal, pyramidal. So this is using Lewis theory, and this is using Vesper theory. And then I have my nitrogen like this, and I draw my three-dimensional picture. So I need to evaluate polarity in 3 dimensions. Otherwise, I'll get this false sense of things canceling out when it's in 2 dimensions. So now I'm going to determine if the bonds in the molecule are polar or not. And so I have, I'll use my electronegativities. So my nitrogen electronegativity is 3.0, and my hydrogen one is 2.1. All of my bonds are between a nitrogen and a hydrogen. The electronegativity difference is equal to that 3.0 minus 2.1, which is going to be 0.9. That falls in that 0.5 to 1.9 range. Therefore, these are polar bonds. So now I'm going to go through and identify those on my molecule. Switch color again. So my hydrogen is less electronegative. So I'm putting the plus symbol pointing to my more electronegative element, nitrogen. And I'm doing that for all of these. I like the dipole arrows like this. All right, so now once I have my polar bonds identified, now what I'm going to do is see if they cancel out or if they give me a net dipole moment. So I'm going to take the vector sum of these dipole moments. And looking at it, I can see that, and I'm going to simplify it here, for any 2, right, there's going to be some element where they're pointing in towards each other, but also going up. So I'll have some that cancel and some that point up. And it's going to happen to all 3 of these. Remember, this is what this looks like, right? So there's a little bit of space that it's actually going, like, pointing up. So a little bit of this will cancel out, but it'll have an overall dipole moment that goes up pointing towards the lone pairs. And so I would call this molecule polar. And that's how I'm going to identify it. Okay. So those are our 3 steps. So once we have our Lewis structure, we build our picture in 3 dimensions, we identify our polar bonds, and then we take the vector sum of our dipole moments to decide if it is polar or nonpolar overall. And sometimes this will be difficult. Sometimes it depends on how we draw the molecule. I'll always grade it based on the way you draw it. All right. So let's go through a few more examples. I have ammonium. We just did this example, and we know that it has an overall dipole moment that's pointing up like this, right? So let's look at these other ones. So let's do bromine and fluorine. So bromine has an electronegativity of 2.8, I'm guessing. It might be 2.5. Fluorine is 4.0. The effect is that this is a polar bond. If it's 2.5 or 2.8, it doesn't make a difference. So that means my electronegativity difference is greater than 0.5. So I have a polar bond between each of my bromines and fluorines. Now, the fluorine is more electronegative. So I'm going to draw that dipole arrow going out like this. Now, another way to draw it, of course, is by putting that partial negative symbol next to the fluorine and the partial positive symbol next to the bromine. This isn't across the molecule, it's across the whole, like just the bond. So if I was going to do that for everything, I would keep that partial positive charge on bromine and put partial negative charges on each of my fluorines. And that would show the reader that I have polar bonds across the board. All right, so now I'm going to try to think about how these cancel out in the vector sum. So what's happening here is these 4 in the equatorial plane that are all in the same plane, these are all pulling opposite directions. And so they're going to cancel each other out, but the one at the top doesn't cancel out. And so the overall dipole moment for this molecule goes along that upward facing or pointing fluorine bond. And so this one will be polar, just like our nitrogen. All right, let's come down to our sulfur and our fluorine. So our sulfur has an electronegativity difference. I think it's 2.5, the same as carbon. I'm doing these from memory, so forgive me. And fluorine is 4.0. So these are all going to be polar bonds because our electronegativity difference is greater than 5 again. So my fluorine is more electronegative. So I'm going to have my arrow point to the fluorine along each of these bonds. And now the question is, how do these cancel out or how do they add up? So I'm going to take that vector sum. I can see these ones that are 180 degrees apart, these cancel out. Now, the other two don't. They're going off in opposite directions like this. So some part of them cancels, but overall they're pointing in the same direction this way. And so I'll have an overall dipole moment that points right in between those 2 fluorine atoms. And this will be polar. All right, xenon and fluorine. We have more polar bonds here. I don't remember xenon's electronegativity, but it's lower in the periodic table than bromine, so it'll be less than 2.8 or 2.5. And fluorine is our most electronegative element. So I'm going to have dipole arrows that are going from xenon pointing to my fluorine. And looking at this, I can see that these two are 180 degrees apart, so they're going to cancel out. Same with these two. So all of my dipole moments cancel out. This is a lot like the carbon dioxide. So this is going to be non-polar. And so because it's nonpolar, I don't draw an overall dipole moment because there's no arrow to point in the direction of a dipole moment. So why do we care about this? All right, and so this is kind of the last piece to molecular polarity. So, and we will dive so much deeper into this, and it's so interesting, but in our next class, attractive forces exist between molecules because, again, attraction is just opposite charges. So the second you say you have a partial positive and negative charge in a molecule, it can interact with other partial or full charges in other molecules. And those attractive forces are pretty strong as they add up within a compound. And so things with those attractive forces, substances, will behave differently than substances that don't have them. And so this is an example right here, of water molecules interacting. And what they do is they line up their partial positive end with the partial negative end of another molecule, and it creates a slight attraction that is stabilizing. And so it's going to be very easy for things that have these partial positive and negative charges to interact with one another. And so they dissolve one another in a solution. And we get this idea that like dissolves like, which really just means that polar molecules will dissolve in polar solvents. And it means that nonpolar molecules will dissolve in nonpolar solvents. So here's the thing. Molecules like oil, which are usually just carbons bonded to other carbons, bonded to hydrogens, and so no polar bonds at all, are nonpolar. Whereas water, we've already shown, is a polar molecule. And so because one's polar and one's nonpolar, they can't dissolve each other. They can't interact. And so they don't dissolve in one another. And so they form layers. And this is why when you have vinaigrette and it sits on the table, it separates into a water layer and an oil layer. And you have to shake it up before you can actually like pour it onto a salad in an evenly distributed manner at all. And so determining if a molecule is polar or nonpolar will tell us which of these layers, oil or water, it would dissolve in. And we take advantage of this so much in organic chemistry. It allows us to crush up some sort of plant, dissolve it in water and oil, shake it up, and compounds in the plant that are oil soluble and nonpolar will go in the oil, and the ones that are water soluble will go in the water, and we can separate them. And this is a way we can isolate certain compounds that might be medicinal or aromatic from a plant.